Hello everyone and welcome to our talk. My name is Andrei Texer and in the next 20 minutes I will tell you about the work I did with my colleagues at CTU in Prague and Snap. We call it interactive video stylization using Fusion patch-based training. Our motivation was to help artists in the tedious task of creating hand-painted animations. We present a framework allowing interactive stylization using single or multiple hand-drawn exemplars. Last year, we presented a paper on stylizing videos by example. From the given video sequence, in this case an Alaskan guy in front of the green screen, we select one frame and let the artist paint over it to produce an exemplar from which the hand-drawn style will be propagated to the rest of the sequence in a semantically meaningful way. Meaning, the same stroke used to stylize an eye in the keyframe are used in other frames as well. In addition, it allows to preserve important high-frequency details typical for used artistic media and maintain temporal coherence. This approach can be applied also to more complicated sequences, where multiple hand-drawn keyframes are used. In this case, a special blending operation to merge stylized content from two different keyframes is used. While this approach is able to deliver state-of-the-art results, there are drawbacks which make it difficult to use in a real production environment, where interactive feedback is inevitable. It's computationally really expensive. For longer sequences, it might take hours. It's sequential, meaning to stylize the current frame, the previous frames needs to be processed first. And last but not least, in the case when there are multiple stylized keyframes available, an entire video sequence has to be processed from the first keyframe and from the second keyframe individually. Then, an explicit blending operation needs to be performed to ensure seamless transition between the sequences stylized using individual keyframes. Our aim is to preserve the high quality of the previous approach. However, at the same time, we would like to preserve interactive experience, meaning to allow the artist to experiment and obtain visual feedback quickly. In particular, we would like to achieve real-time inference, at least 10 frames per second, allow for random access to the individual frames, and avoid explicit merging of sequences stylized using different keyframes. In fact, we would like everything to be as implicit as possible. To approach this challenging task, we draw inspiration from the recent success of image translation networks, for example Stylization by Fuchik and his colleagues, which is able to perform semantically meaningful style transfer to faces. This approach is capable of delivering high-quality stylized results in real time, but it requires a huge dataset for training. When we apply Stylization directly on our task, meaning we train the image translation network on a single training pair, what happens? As can be seen, the first image of the video sequence is stylized correctly, but when we play the video to see the other frames, they have poor quality and are quite noisy. No wonder actually, the network is strongly overfitted to the single training sample. Well, let's give it another try and use data augmentation techniques. We tried many traditional data augmentation techniques, and the following are the results on the fifth frame of the video sequence. We try to add Gaussian noise to the input. We try to add salt and pepper noise to the input, occlude some parts of the image, use dropout, and other regularization and data augmentation techniques. The results were slightly better than before, but still far from what we would consider comparable quality to the state-of-the-art method of Jamriška and his colleagues. To elevate this issue, we got inspired by recently published work of Zhou and colleagues, non-stationary texture synthesis by adversarial expansion, and use a patch-based training strategy to simulate a large dataset that is needed by image translation networks, in our case, Stylization. We randomly sample small patches from the single training image and use them to train the network. We take an input image, we sample patches from it. We run the patches through the network. We sample patches from the corresponding locations of the output image, and we compute the loss between these patches, and we backpropagate the error. As described in Stylization, we use L1 loss, adversarial loss, and perceptual loss, but our patch-based training strategy is not limited to any particular losses. During the inference, since we aim for inference speed, we cannot do this on patches, But thanks to the fact that our network is fully convolutional, it only has convolution layers, we can feed an entire input image and pass it through the network to get a stylized result. Moreover, since we do not have any data dependency, meaning we can stylize random frames from the input video without the need for any other frames, we can stylize the entire video in parallel. We can sample, for example, 20 frames and run them through the network at once in a single batch. So, how does the result look with batch-based training? It's better, but it still doesn't achieve comparable video quality to Jamriška and his colleagues. See the comparison. To further refine the results, we need to tune the hyperparameters. But we do not have any ground-truth data to validate our network on. We just have one hand-painted style exemplar used to train the network. To alleviate this lack of information, we propose to use our last year's video style transfer approach to generate the ground-truth data. Note that this has to be done only once for hyperparameter tuning. Once the hyperparameters are optimized, the method of Jamriška and colleagues is no longer needed. To perform the hyperparameter tuning, we use grid search. We sample size of individual patches, number of patches in one batch, number of ResNet blocks, and learning rate. Since we aim for interactive response, we impose a strong constraint on the training time to be less than 1 minute. Once the network is trained, we validate it as follows. We run the image through the network, in this case, on frame number 5. We take the generated image and ground-truth image and compute the loss. We use N1 loss and perceptual loss. According to those measurements, we found that the batch size is a crucial parameter and that the best quality is obtained when the batch size is relatively small, 40 patches in one batch. One might think that the batch size would not matter at all, or that there should be as many patches in one batch as fits to the GPU memory. But in the loss curve, there is an obvious minima and quality difference between batch size of 40 patches and batch size of 500 patches is huge. This makes sense, since with an increasing number of patches in one batch, we would eventually end up with full frame training. Whereas, if the number of patches in one batch is small, it increases diversity of gradients that are backpropagated and the network is less likely to overfit. We also found that patch size is an important hyperparameter as well. Initially, we thought that the optimal size of training patches would strongly depend on the given artistic style. However, it turned out that size of 36 by 36 pixels is a good default for a variety of styles. Lastly, we also tried to change the depth of the network by increasing or decreasing the number of ResNet blocks, and we found that this hyperparameter doesn't really make much of a difference, as long as it is set in a reasonable range between 1 and 20. And here is a comparison before and after the hyperparameter tuning, and as can be seen, the quality has significantly improved. Moreover, since we optimize hyperparameters for 1 minute of training, the training converges really fast. Here's the setup. We have input keyframe and its stylized version, and here is the other frame from the sequence. And after just few seconds of training, we obtain already faithfully looking images. Now, we have all the hyperparameters set correctly, and we can run the synthesis and enjoy the results. Or not? Well, the output video flickers. It's not visible by the naked eye, but the input video sequence has some subtle noise and the network amplifies this noise. So, we can filter the input sequence using motion compensated bilateral filter in the temporal domain. And here's the filtered sequence and the new result. It flickers less, but it's still not perfect. And why is that? Well, it's because there's ambiguity during the training. And what do I mean by ambiguity? We train the network to map an input image to an output image, and we train it on small patches. These two input patches have exactly the same color, but their corresponding output patches have different colors. The green patch is more whitish, while the orange patch is more bluish. And this, of course, confuses the network during training. So we propose to add an auxiliary input layer with a mixture of randomly generated colored Gaussians. The input to our network has now 6 color channels, which ensure that all patches have unique content. But how is this Gaussian mixture layer generated? Let's see it on a sequence with slightly more motion. We generate random colored Gaussians for one frame of the sequence, marked in yellow here. To propagate the colored Gaussians into nearby frames, we use as rigid as possible image registration technique of Siggraph and his colleagues. It helps us to estimate dense correspondences between individual frames and move the colored Gaussians to their corresponding locations. But after a while, there are holes. So we pick another frame and we do exactly the same. And we do this for 2 more frames. In this case, we use totally 4 different frames. And to make the final Gaussian mixture layer, we simply stack these intermediate Gaussian mixtures on the top of each other, and black holes are transparent. Now, we are able to stylize videos with high visual quality and temporal coherence. And you are eager for more results, I'm sure of that. But allow me to mention another important feature of our approach. In the case where we have an input video with substantial motion like this one, using one style exemplar shown above, the result looks like this. The frontal face is okay, but it breaks when she rotates her head. The network is designed to follow the provided style exemplar precisely, so if there is new content, we have to provide another style exemplar. Side view. And now it works fine. Note that our framework not only handles multiple style keyframes without any explicit blending, but it also is very efficient. Thanks to our patch-based training strategy, an artist does not have to paint the entire second style frame. Only thing that needs to be painted is the problematic part, and during the training we restrict the patches to be sampled only from the newly painted areas, in this case marked in red. And now it's time for some results. All results here were stylized using one hand-painted keyframe. We compare each sequence with the approach of Yamishka and his colleagues to ensure that we provide comparable visual quality and temporal coherence, while we offer fast inference, random access to individual frames, and interactive experience. The results here were stylized using multiple keyframes. This one was stylized using 4 keyframes. The link sequence has 2 keyframes. Here, 3 keyframes were used. And since this sequence has a lot of motion, 6 keyframes were used. And here, 2 keyframes were sufficient. And since our approach is really fast in terms of both the training and the inference speed, it allows us to come up with various interactive scenarios, which are very engaging for artists. Here, my colleague pre-recorded herself. She printed 2 keyframes on a stencil, and now, while she is painting, the training and inference runs, and a pre-recorded video reflects the newly painted changes on the fly. And now she just switched to the second side view keyframe. Here, the setup is similar, but the pre-recorded sequence is different. In this setup, a live feed from the video camera is being stylized, while my colleague is digitally painting over one captured keyframe in Photoshop. And most importantly, we release the source code. So please be sure to check our project page for the GitHub repository, more videos, and other material. And finally, we shall set up with 2 live camera feeds. One camera feed to capture the painting, and the second front-facing camera to capture the artist. All changes she made are quickly reflected in the input video stream. Thank you very much for your attention.